You know, have you ever typed a website address like example.com into your browser and bam, you're just there almost instantly?
Yeah, it really feels like magic, doesn't it?
It totally does. It's this piece of tech, so fundamental, so deeply embedded in, well, everything we do online that we hardly ever stop to think about it. But it's underpinning absolutely everything, you know, checking email, streaming shows, running huge businesses.
It's the silent workhorse.
Yeah.
And that invisibility, that's kind of what makes the domain name system, or DNS, so fascinating. People call it the core addressing fabric of the internet. And its job is just monumental, really, turning those names we can read,
Like example.com.
exactly,
Yep.
into the IP addresses machines need to actually find each other. It's performing this translation billions, maybe trillions of times a day globally.
Yes. Wow. Okay, so today our mission is to really take a deep dive, right? We
Yeah.
want to go way beyond just the basics of that translation. We're pulling back the curtain to see how this magic is being fundamentally reshaped. There are these huge forces at play.
Yeah, big shifts happening.
And crucially, why understanding all this is more critical now than maybe ever before. It's not just for the network nerds anymore, is it?
Not at all. It's becoming really strategic for basically any organization.
So where are we getting our insights from today?
Our main source is this really comprehensive piece, the Comprehensive Research and Analysis Report, 2025 edition, focusing specifically on DNS.
Okay.
And it digs into the most important insights, some really unexpected facts, and the practical side of things, too. What it shows is that while, yeah, the basic DNS structure is from '83.
Pretty old in tech terms.
Right. But the ecosystem around it, it's been undergoing this massive, continuous transformation, especially over the last, say, 10 years. It's like a quiet revolution happening under the surface.
And the report talks about the magic of DNS in two ways, which I found really interesting. First, there's the magic we feel, right? That user-perceived magic of just instant connection, type, click, boom.
Yeah, the seamless experience.
But then there's the other magic, the engineering magic. The report calls it that.
Ah, yes. The deep stuff.
Exactly. The
Yeah.
super sophisticated, dynamic, secure, policy-driven naming layers working behind the scenes. That distinction, that's where it gets really fascinating, I think. It shows that simple feeling rests on some seriously complex engineering.
It absolutely does. Intentionally engineered complexity hidden away.
But let's unpack that core concept a bit more. We often hear DNS called the phone book of the internet. Simple enough.
That's a decent starting point, yeah.
But the report uses a slightly more technical term, a hierarchically distributed naming system. Sounds a bit more involved. Can you break that down? What does hierarchically distributed actually mean in practice?
Sure. So imagine that global phone book, but instead of one massive, unwieldy book.
Which would be impossible to manage.
Right. It's actually millions of interconnected smaller books or databases, and each one is only responsible for a specific slice of the internet's names. Hierarchically distributed means there's no single central server that knows everything.
Okay.
Instead, the authority, the knowledge of who owns which name, is delegated downwards in layers.
Layers, like an organization chart.
Kind of, yeah. At the very top, you have the root servers. Think of them as knowing where the main librarians are the ones managing the big sections like .com, .org, or country codes like .uk.
Got it. So the root knows who manages .com.
Exactly. Then those top-level domain servers, the TLD servers for .com, they know who's responsible for the specific domains under them, like example.com. They point you to the authoritative name servers.
The final source of truth for that specific domain.
Precisely. They hold the actual records, the IP address for example.com.
Okay, so that whole journey of finding the IP address, that's resolution, right?
That's the term, yes. Resolution. When you type example.com, your computer doesn't know the IP, so it asks a recursive resolver.
That's usually my ISP. Or maybe Google's 8.8.8.8.
Often, yes, or Cloudflare's 1.1.1.1 or others. This resolver then goes on a sort of quest, asking questions step by step.
Okay.
It might ask a root server, hey, where do I find info on .com? The root says, go ask this TLD server.
Right.
Then it asks the .com TLD server, okay, who's authoritative for example .com? The TLD server gives back the address of the authoritative server.
And then it finally gets the IP address.
Exactly. The resolver asks that authoritative server, what's the IP for example.com? Gets the answer and passes it back to your browser.
And this all happens in milliseconds.
Typically, yeah. It feels instant, but there's this whole chain of queries happening incredibly fast.
It really is that invisible engineering magic right there. Wow. And it's not just about mapping names to IP addresses, those A or AAA records, is it? The report mentioned other resource records.
Oh, absolutely. DNS is way more versatile than just address lookups.
Right.
Those A records for IPv4 and AAA for IPv6 are fundamental, sure.
There's more.
Definitely. You've got MX records, crucial for email. They tell mail servers where to deliver email for, say, example.com.
Okay, mail exchange. Makes sense.
Then TXT records. These are super flexible, just text fields, used for all sorts of things. Email security, like SPF and DCAM, proven you own a domain for Google Search Console.
Huh, versatile.
Very. NS records point to the authoritative name servers themselves. CNAMEs create aliases, like making www.example.com point to just example.com.
Useful.
SRV records help locate specific services, like maybe a voice chat server or a specific game server. And really importantly now, we have newer types like SVCB and HTTPS records.
What do they do?
They're about improving service discovery, especially for newer stuff like HTTP3. They let your browser find out preferred connection methods or alternative servers directly via DNS. So it's constantly evolving, adding new capabilities.
It's incredible how far it's come, especially considering its beginnings. The report mentions it started even simpler than that 1983 standard.
Oh yeah, much simpler. Way back in 1973, the first attempt was literally just a single text file, host.txt.
One file. For the whole internet.
Well, the early ARPANET, yeah.
Yeah.
Maintained manually by the Network Information Center, the NIC.
Yeah.
If you added a computer, you emailed them, they updated the master file, and everyone else had to download it periodically.
Wow. Wouldn't scale well.
Not at all. Completely unmanageable. That's why RFC 882 and 883 in 1983 were so revolutionary, introducing the distributed hierarchical system we still largely use today.
And key milestones since then.
Big ones include the root server Anycast expansion starting around 97, those 13 logical root servers. They now run on hundreds of physical instances globally using Anycast routing. Huge for performance and resilience.
Right, spreading the load.
Exactly. And then DNS-SCC standardization in 2004, aiming to add security. Though, as the report points out, adoption was pretty slow for a long time.
We'll definitely come back to that. So, digging into the core engineering principles, what makes DNS so robust? The report mentioned pillars, right?
Yes, several key pillars enabling that magic. First is hierarchical delegation, which we touched on. The root doesn't know everything. It delegates .com, which delegates example.com. Each part, each zone file, is only authoritative for its own little piece of the namespace.
That's the scalability key, isn't it?
Absolutely. It prevents bottlenecks and single points of failure, makes the whole system incredibly resilient. Second pillar, caching and TTL, time to live, super important. When your recursive resolver gets an answer, it caches it locally for the TTL period.
So it doesn't have to ask all those servers again next time?
Exactly. Saves time, reduces load on the upstream servers. Now, the report had this interesting finding about TTLs.
Oh, yeah?
Empirical research shows that setting TTLs really low, like under 600 seconds, 10 minutes, it actually has only a modest impact on how often the cache can answer directly, the cache hit rate.
Huh. So shorter isn't always drastically better for performance.
It seems not dramatically so. And setting them too short increases the load on authoritative servers. So there's a balance. Longer TTLs can actually improve overall system efficiency by reducing redundant queries. It's a trade-off.
That's counterintuitive, but makes sense. Over-optimizing TTLs could actually backfire by hammering your own servers.
Precisely. It can increase costs, vulnerability to denial of service, maybe even slow things down if your servers aren't scaled for constant queries. A small detail with big consequences. Third pillar, transport flexibility. DNS used to be mainly UDP port 53 for SMED, with TCP 53 as a backup for bigger responses.
Right, the standard ports.
But now, driven by privacy and security concerns, we have this whole new suite of encrypted protocols. DNS over TLS, or DOT, on port 853.
Encrypts the query.
Yep. Then DNS over HTTPS, DOH, on the web port 443. Wraps DNS and normal HTTPS traffic.
It makes it harder to spot or block.
Exactly. And the newest one, DNS over QUIC DQ, also usually on UDP 853, standardized in 2022.
So why so many? Just different ways to encrypt.
Pretty much. It's about increasing privacy, stopping eavesdropping by ISPs or others, and for DOH, blending in with web traffic to bypass censorship or filtering. Different approaches for slightly different goals. And the fourth pillar, security via signing and validation, which is primarily DNSCC.
Okay, this sounds critical.
It is. It adds integrity and authentication. Basically, proving the DNS data hasn't been tampered with and comes from the legitimate source.
How does it do that? Magic signatures?
Kind of. Cryptographic digital signatures are added to the DNS records. New record types store these: RSIG, DNSKI, DS, and a CC3.
Okay.
A DNSCC-aware resolver checks these signatures, validating them against trusted keys, ultimately tracing back to the root zone's key. This prevents attacks like cache poisoning.
Where someone tries to feed fake addresses to the resolver.
Exactly, redirecting you to malicious sites. DNSSEC aims to ensure the phone book entry itself is authentic and untampered with.
Okay, taking all that foundational stuff, what does it mean for businesses today? Why is this suddenly a strategic thing, not just IT plumbing?
Because, simply put, DNS availability is business continuity. It's revenue. The report has a stark number.
Yeah.
A single 30-minute authoritative DNS outage. It can slash daily e-commerce sales by 4-6%.
Wow. Half an hour and you lose that much.
It's a direct financial hit. Plus, think about brand reputation. If your site's down, trust erodes quickly.
And then there's the privacy side you mentioned.
Right. Huge pressure from regulations like GDPR, CCPA, plus concerns about nation-state surveillance, data sovereignty law.
Companies need more control.
Exactly. They're pushed towards encrypted DNS, towards sovereign DNS stacks where they control the data flow and privacy. It's not just, is my site up anymore? It's, how is it accessed? Who sees the patterns? Where does the data live? Mastering this DNS magic, the protocols, security, the market, it's absolutely mission critical now. It's about trust and resilience.
That really sets the stage. Okay, so the report identifies these 5 macro forces that have really shaken up the DNS world over the last decade. These sound like the big drivers of change.
They absolutely are. They explain why DNS isn't static. It's evolving dramatically.
Let's break them down. What's the first one?
Force number 1 is the sheer scale of hyperscale, cloud, CDN, and edge adoption. Basically, everyone moving everything to the cloud, using content delivery networks, pushing computing power closer to users at the edge.
All that decentralization and scaling up.
Right, and it's driven DNS traffic through the roof. The numbers are just astronomical. The report estimates over 1.1 times 10 to the 12th queries per day.
That's, wait, over 1 trillion DNS lookups every single day.
Over 1 trillion. Daily. It's an unbelievable volume. And this scale demands a DNS system that's not just massive, but incredibly fast and reliable.
And the result of meeting that demand, what does that mean for us?
It means speed. Median resolution times in mature markets are now below 20 milliseconds.
20 milliseconds, that's basically instant. Imperceptible.
Exactly. It means the DNS lookup itself adds virtually no delay to loading a web page or using an app. It's a huge part of that seamless magic we feel. That speed is engineered.
Okay, force number 2.
Security hardening. This is a big push, an acceleration really, to make DNS fundamentally more secure, building on things like DNSSEC, but really focusing now on encryption.
So DNSSEC, DDoT, DDo, H2Q, all that stuff we touched on.
Precisely. After years of somewhat slow uptake, especially for DNSSEC, we're now seeing much faster adoption of the encrypted protocols.
What's driving this sudden urgency for security? It feels more intense now.
Several things are converging. The report points to 1, regulatory pressure governments demanding better data security and privacy.
Makes sense.
2, the big shift in IT towards zero-trust security models. Trust nothing, verify everything. That means even DNS queries need securing.
Okay.
And 3, a major driver. A big rise in DNS-based DDoS attacks. They're getting nastier, bigger, peaking at 1.29 million queries per second in a 2023 attack.
1.3 million queries per second. That's insane.
It's a huge amount of malicious traffic aimed squarely at DNS infrastructure. It forces defenders to harden their systems.
Okay, but here's the kicker, right? The report says, despite all this, DNSSEC adoption is still surprisingly low.
It is, and it's a bit baffling on the surface. Only about 6% of 171 million domains analyzed were actually using DNSSEC signing, even though the root and TLDs are signed.
So what gives? Why isn't everyone using this critical security feature? What's the holdup?
It really comes down to real-world friction. The report highlights operational complexity, what they call key role paying.
Key role paying. Sound unpleasant.
It can be. Managing and rotating the cryptographic keys for DNSSEC securely is complex. Get it wrong, and boom, your domain stops resolving for everyone trying to validate. Outages are a real risk.
So a fear of breaking things.
That's a big part of it, especially for organizations without dedicated security teams. Plus, there's often a limited perceived ROI. DNSSEC secures the data's integrity, which is vital, but maybe not as immediately obvious a benefit to an end user as, say, an encrypted web connection via HTTPS.
So it's hard, potentially risky, and the benefit isn't always clear to management.
That sums it up pretty well. It's a classic security implementation challenge. Now, contrast that with encrypted DNS, DOT, and DOH. The report says they are crossing the early majority chasm. Over 70% of traffic from browsers like Firefox, Chrome, and on iOS prefers encrypted DNS by default in many places.
Whoa, that's a huge difference, 70% versus 6%. Why is encrypted DNS taking off so much faster?
It's a fascinating contrast, isn't it? It really boils down to ease of use and perceived benefit.
How so?
Encrypted DNS, especially DOH, gives users an immediate, understandable privacy win. Your ISP can't easily snoop on your browsing habits via DNS lookups.
Right, that's a clear benefit people get.
And crucially, browsers and operating systems have made it super easy to enable. Often, it's the default setting now. Users don't have to do anything complex.
Frictionless adoption.
Exactly. Whereas DNSSEC puts the burden on the domain owner to implement and manage those complex keys. Its benefit, preventing cache poisoning, while critical for internet health, feels less direct to the average user or small business owner. So the easier thing with the more obvious immediate benefit wins the adoption race, for now.
That makes a lot of sense. Okay, force number 3. This one's about the market itself, right?
Yes. The rise of managed and cloud DNS services. This isn't just about tech, it's a massive business shift. The report values this market at USD $2.3 billion in 2024.
$2.3 billion.
And growing fast. An 8.5% compound annual growth rate projected to hit USD $5.1 billion by 2033. More than doubling.
Wow. Who are the big players driving this?
The usual suspects in cloud and infrastructure. Cloudflare, Google, AWS, Microsoft, Akamai. They're offering incredibly high-performance authoritative DNS. We're talking global medium response times under 11 milliseconds.
Blazing fast. Well, what's driving companies to switch from running their own DNS?
Economics, mainly. These managed services use consumption pricing pay for what you use, which fits the cloud model perfectly. And the TCO, the total cost of ownership. It's compelling. The report benchmarks it. Moving from running your own bindy servers on-premise to a global space. Any CAS service can cut your TCO by 32% to 47% if you're doing around 10 billion queries a year.
That's a huge saving.
It is.
Yeah.
And you often get a 100% uptime SLA thrown in. Better performance, higher availability, lower cost. It's a very attractive proposition for many. It delivers that enterprise-grade magic without the headache and expense of building it yourself.
Okay, force number 4 hits that intersection of politics, law, and technology. Privacy and sovereignty pressures. GDPR, CCPA, national laws.
Yeah, this is having a very direct impact. Look at WHOI's data, who owns a domain. Used to be mostly public.
Right.
Now, the report finds 58% of generic TLD domains are behind privacy proxies or registrar redaction services. Privacy rules make that old transparency difficult.
So ownership info is often hidden now.
Largely, yes. And this push for privacy, plus national desires for data sovereignty, keeping data within borders, forces enterprises to rethink their DNS architecture.
Wow.
It leads them towards things like split horizon or private DNS. Basically, handling internal DNS lookups securely and privately within their own network, maybe using encrypted protocols, while letting external queries go out to public resolvers. It gives them control, ensures privacy for internal stuff, and helps meet data residency rules.
Makes sense. Adapting the architecture to the legal landscape.
Yeah.
Okay, the 5th and final macro force, it sounds a bit different. Innovation at the last mile, beyond the traditional hierarchy.
This one is really interesting. It's about naming within specific networks or applications, moving beyond just relying on the global public DNS for everything.
Like for internal stuff.
Exactly, or for peer-to-peer setups.
Fair.
The report uses Tailscale's Magic DNS as a prime example.
Ah, I've heard of that. For secure networking.
Right. It lets devices within a Tailscale network find each other using simple, human-readable names, securely, peer-to-peer, without needing to register those names in the public DNS.
So it's like a private internal DNS.
Sort of, but often more dynamic and integrated. It's part of a broader trend the report calls application-defined naming. The application or the overlay network itself handles the name resolution, abstracting away the underlying, often changing IP addresses.
So my service database prod can always be found at that name by my web app, even if its IP changes constantly.
Precisely. The overlay network manages that mapping. It's a new kind of magic, especially useful for modern distributed systems, microservices, remote work, offering simplicity and security for that internal or east-west traffic.
Okay, so we've got these powerful forces driving innovation, performance, security, but the report is clear. DNS is still a major risk point, right? Still vulnerable.
Absolutely. It remains a critical point of failure. We can't forget incidents like a 2016 Mirai botnet attack on DIN.
Oh man, that was huge. Took down Twitter, PayPal, Netflix. Big chunks of the internet felt broken.
It was the largest single provider failure on record. A real wake-up call about DNS fragility.
But here's something worrying the report found. Are we actually more vulnerable now in some ways?
It's a concerning finding. The report indicates that today, 5% more top websites rely on a single DNS provider than did back in 2016.
Way more. After seeing what happened with DIN, why would companies increase their reliance on a single provider?
That is the crucial question, isn't it? It suggests that maybe the lessons about redundancy haven't fully stuck. Perhaps the convenience, cost savings, or perceived simplicity of using one provider are overriding the resilience argument for some. It definitely raises questions about whether we're learning from history.
It seems like a recurring theme, convenience versus robustness. And the threats themselves aren't standing still either, are they? The report mentions next-gen attacks.
No, the attackers are constantly innovating, too. We're seeing things like carpet bombing bits and pieces floods.
That's ominous. What is that?
Instead of one massive flood, it's lots of smaller, distributed streams of malicious queries hitting many targets subtly, trying to fly under the radar but overwhelm systems cumulatively.
Sneaky.
Very. Then there's still DNS tunneling, sneaking data out by encoding it in DNS queries, bypassing firewall.
Data exfiltration via DNS.
Yep. And also machine-generated subdomain attacks, bots, creating floods of queries for random, non-existent subdomains to exhaust resolver resources.
Like random123.example.com, random456.example.com, over and over.
Exactly, millions of them. These aren't just theoretical, they're happening now. They demand faster, smarter defenses, AI-assisted anomaly detection, real-time rate limiting right at the edge. You need proactive defenses.
Okay, so the risks are real and evolving.
Yeah.
But the report doesn't just point fingers, it offers solutions, right? Strategic recommendations for building a more resilient DNS setup.
Yes, absolutely. It provides clear, actionable guidance. Let's walk through them. Recommendation number 1. Adopt dual authoritative providers. This is huge for resilience.
Meaning, don't put all your eggs in one basket. Use 2 different DNS companies.
Exactly. Use at least 2 distinct providers, ideally on different networks, and set up automatic zone transfer so they stay in sync. Think Cloudflare plus NS1 or AWS Route 53 plus Akamai, for example.
And the benefit.
Eliminate single vendor risk. If one provider has an outage, the other keeps you online. Plus, you can often get even better global performance, that sub-20 millisecond RTT, by leveraging both networks. It's basic redundancy, but critical. Second recommendation. Enable DNSAC signing and mandate validation on your internal resolvers.
Okay, back to DNSAC, but tackling that key role pain.
Yes, the key is automation. The report stresses automating the KSK and ZSK, the key signing key and zone signing key rollovers. Use standardized methods like RFC 8078, CDS, CDN, CC, or your cloud provider's API tools for rotation.
So take the risky manual process out of it.
Precisely. Automation prevents those misconfigurations that lead to validation failures and outages. Make the secure option the easy, automated option. Third, transition user endpoints to encrypted resolver protocols, DOT, DOH, and DQ.
So encourage users, but also manage it on the network side.
Exactly. Enterprises need to permit the necessary ports, like 853 UDP TCP. But crucially, they also need to implement egress allow lists for known, trusted DOH-DOQ endpoints.
Hi, the allow list.
To prevent those blind spots where malicious actors could set up their own DOH servers for data exfiltration, bypassing your security, you control which encrypted resolvers are allowed. It also pairs with split horizon DNS for keeping internal queries private. Fourth recommendation, instrument real-time DNS analytics. Don't treat DNS logs as an afterthought.
Treat DNS data like any other critical monitoring signal.
Absolutely. Feed DNS query streams into your security monitoring system. Set up real-time alerting for anomalies in query rates or types.
What kind of anomalies?
Sudden spikes in queries to non-existent domains might signal a DDoS attack. Weird query types could indicate tunneling. You need to see these patterns proactively to catch threats early, turn that data into actionable intelligence. And the fifth strategic recommendation, integrate zero-trust naming layers.
Like the Magic DNS example, decoupling naming from IP addresses.
Exactly. Using systems like Tailscale Magic DNS or SPIFE IDs, in a zero-trust world, you don't trust the network. Services need to find and authenticate each other based on strong identities, not just IP addresses.
So Service A knows it's talking to the real Service B, regardless of where Service B is running.
Correct. It massively improves security for that internal east-west traffic. Even if an attacker gets inside your network, they can't easily discover and target services just by scanning IPs. SPIFE IDs, for instance, give services cryptographic identities for mutual authentication.
Okay, so those are the big strategies. The report also gets down to specifics, right? Like
Yeah.
common problem, direct mitigation.
Yeah, it offers very practical pairings. For those huge DDoS floods like 1.29 MQPCs, mitigation is primarily using Anycast authoritative services to absorb the load, combined with aggressive rate limiting and response rate limiting, RRL. Spread the pain, block the noise.
Makes sense.
For cache poisoning Kaminsky attacks, mitigation is DNS SEC validation to ensure data integrity, plus potentially using a zero TTL defense in critical cases to force resolvers to always fetch fresh, validated data.
Okay, verify everything.
If you hit slow magic DNS lookups on specific OKeys like Windows, Mac OS, mitigations involve things like installing helper components, LIMS resolve, always using fully qualified domain names, and keeping clients patched. Basic operational hygiene.
Right, fixing local issues.
Tackling operational key role issues with DNS SEC.
Yeah.
Mitigation is automation, automation, automation. Using RFC ADS78 and CDS-CDN-ST mechanisms to avoid manual errors during key rollovers.
Let the machines handle the tricky bits.
And preventing shadow IT DUH tunnels for data exfiltration. Mitigation requires layers DNS firewalls to inspect traffic, strict egress policies controlling outbound connections, and those explicit DOH allow lists we mentioned. Monitor and control all exits.
This is all super valuable technically, but let's bring it back to the business impact. How does investing in modern DNS actually pay off? We need the ROI, the success stories.
The report provides some really strong data points on that. It references a 2024 Forrester Total Economic Impact study looking at companies that migrated to managed Anycast DNS.
What did they find?
They found, on average, a reduction in annual downtime of 7.3 hours. Now, that might not sound huge.
But for a business, 7 hours of downtime can be massive.
Exactly. It translated directly into a $1.2 million productivity gain annually for those studies.
1.2 million, just from better DNS uptime.
Yep. And looking longer term, the 3-year net present value, the NPV, of making that switch was $4.6 million. That compares really favorably to the $1.8 million NPV of sticking with on-premise solutions.
So a much better return. And
Yeah.
how quickly did they see that return?
That's maybe the most impressive part. The payback period was less than 8 months. You start seeing the financial benefits really fast.
Under 8 months, it's a quick win for infrastructure investment. Are there specific company examples that bring this to life?
Definitely. The report highlights a couple of great ones. Grafana Labs, the observability platform. They cut their VPN configuration time by 90%.
Yeah.
90! After rolling out Tailscale Magic DNS, they achieved LAN-like discovery across 1,500 nodes. Think of the developer hours saved.
Huge productivity boost right there.
Absolutely. And then there's DigitalOcean, the cloud provider. They face multiple massive DDoS attacks over 1 terabit per second each.
Wow.
And they credited Cloudflare Foundation DNS, their managed provider, with absorbing those attacks completely. 0 downtime. That's resilience under extreme fire, protecting their entire platform and all their customers. Real-world proof. Now, the report also does a good job comparing the different types of DNS solutions because it's not one size fits all.
You're right, helping people choose.
Exactly. So on-premise bind clusters. Pro is full control, no recurring fees after setup. Con is high upfront cost, CapEx, limited global reach. Anycast is hard DIY. And you bear the brunt of DDoS attacks yourself.
Okay, old school, lots of control, that's a work.
Pretty much. Then DIY Anycast with BGP. Pro is vendor neutrality, build it all. Con is it requires deep networking expertise, complex BGP management, and high costs for global server colocation. Really only for the big players.
Very high barrier to entry.
For sure. Then blockchain DDNS, like Handshake or ENS. Pro is censorship resistance, decentralized control. Con is currently low adoption, potential performance latency due to blockchain lookups. More niche right now.
Interesting concept, not quite mainstream.
And finally, overlaying naming like MDNS or Magic DNS. Pro is great for private networks, no public registration needed, simple for internal use. Con is the scope is limited, only works within that local network or VPN mesh, not for public websites.
So based on those trade-offs, the report gives a kind of decision framework. Like, if you're this, use that.
Yeah, it provides some clear starting points. If you're a global public brand needing top performance and security, go with managed authoritative DNS plus DNS SEC. Leverage those global Anycast networks and sign your zones.
Makes sense for visibility and trust.
If you have high security internal services, use Split Horizon DNS plus DDoT DOQ validation. Keep internal lookups private and verified. Handle public separately.
Control and privacy internally.
For developer PDP labs or agile environments, Magic DNS or MDNS works well. Simple, dynamic, localized naming.
Keep it simple for dev teams.
And if you're an anti-censorship activist or need to bypass filtering, explore DDNS or DNS over Tor for that decentralized resistance.
Choose the tool for the specific job and threat model.
Got it. Okay, looking ahead, what's next? What does the crystal ball say for DNS between now and, say, 2030?
The report highlights several key trends shaping the future. First, DoQ mainstreaming. DNS over QEIC is expected to handle over 25% of resolver traffic by 2027. Mobile providers really like it because QUIC handles flaky mobile connections better than TCP or traditional UDP. Better performance, better privacy on mobile.
Okay, QUIC takes over more DNS.
Second, AI-driven anomaly detection gets built in. Recursive providers will use machine learning to spot threats like tunneling or fast flux attacks almost instantly under a second. Smarter, faster, automated defense. DNS getting its own AI security guard.
Kind of, yeah. Third, sovereign DNS clouds become more common. Think national DNS infrastructures, like the proposed India DNS, forcing resolution paths to stay within the country for data sovereignty reasons.
More national control over DNS data flow.
It could lead to that, yes. Fourth, and this is really cool, DNS as data bus. New standards like SVHTTPS records will let DNS do more than just return an IP.
Like what?
Like telling your browser about service capabilities. Hey, this server prefers HTTP3, or here are parameters for connecting via mask. DNS becomes a richer service discovery mechanism, not just an address book. It advertises how to connect best.
Whoa, that's a big shift. DNS telling apps how to talk to each other.
It's a fascinating evolution. And finally, looking further out, quantum-resistant signatures. The IETF is expected to start standardizing post-quantum algorithms for DNS-SEC around 2028.
Planning ahead for quantum computers breaking current crypto.
Exactly. Future-proofing DNS-SE to ensure the integrity of the Internet's naming system stays secure even against quantum threats. Long-term planning for a fundamental protocol. Hashtag tag outro.
Wow. We have really gone deep into this magic of DNS, from the basic ideas and the history right through to these huge forces changing everything and what looks like a really dynamic future. It's just crystal clear that DNS reliability, security, performance, it's not just background noise. It's absolutely fundamental to digital trust, business survival online.
It really is. And that core message from the report really resonates. That magic that used to hide the complexity, now it demands intentional engineering. You can't just set it and forget it anymore.
Right, you have to actively manage it.
Yeah. Organizations need to turn DNS from this potential invisible weakness into a strength, something resilient, secure, and actually providing useful insights. That means adopting things like dual providers, automating DNS-SCC, encrypting everything, using those analytics, taking conscious control.
Make it a platform, not just a utility.
Precisely. Convert it from a liability into an asset.
So for everyone listening, now that you've heard about this incredible complexity, this constant evolution, the vital role DNS plays, how might you look at your next click, your next website visit, differently? What part of this deep dive into DNS magic will you maybe dig into next? Perhaps how your own phone handles DNS, or whether your company uses DNS-SCC.
Yeah, we really hope you'll think about the critical, often unseen work this system does every second of your digital life. Its ongoing evolution, driven by security needs, privacy demands, sheer internet growth is what keeps our connected world working reliably and securely. It truly is the silent, constantly adapting magic behind it all.